In this example, we're going to solve a system of differential equations where the matrix is diagonalizable. So the question asks, find the general solution of x prime equals ax, where a is this matrix, where the first row is 0, 1, 1, second row is 1, 0, 1, and the third row is 1, 1, 0. So in the previous video, I actually calculated the eigenvalues and eigenvectors of this matrix, and I found that for one of the eigenvalues, -1, I found two independent eigenvectors, v1, which is 1, -1, 0, and v2 equals 0, 1, -1. Again, there are lots of choices for independent eigenvectors, but this is an easy choice. And then for the other eigenvalue, which is 2, I found one eigenvector, which is 1, 1, 1. So in that video, I went over the calculation of how to find this. So once we have this, we can find the general solution. The general solution is x is c1 times 1, -1, 0, e to the minus t, right? Because I have the eigenvalue -1, plus c2, and then I have v2, 0, 1, -1, e to the minus t, plus, and then c3, v3, e to the e to the 2t. So that's the general solution for all constants c1, c2, and c3. So notice that we have a repeated eigenvalue, -1, right? That has a multiplicity of 2, but we were still able to find the general solutions because basically as long as the matrix A is diagonalizable, you're able to find independent eigenvectors, and it's really the n independent eigenvectors that you need. So once you have the n independent eigenvectors, you can write down the general solution. So remember that for a matrix, if it's diagonalizable, okay, you might not have distinct eigenvalues, but you might not have n distinct eigenvalues, but as long as the geometric multiplicity is equal to the algebraic multiplicity, then you will get n independent eigenvectors. So the general procedure is, in general, if A is diagonalizable, then find a basis of eigenvectors for each of the eigenspaces, right? Or for each of the eigenvalues. So with eigenvalues λ1 through λk, then choose an eigenbasis. So choose a basis, choose bases for each eigenspace. Okay, so that just means find the basis of eigenvectors, right, for each eigenvalue that span the space of eigenvectors. So choose bases for each eigenspace, and for each basis, so let's say λ1 gives you a basis, I don't know, v1,1 to v1k, let's say, and then λ2 gives you a basis v2,1 to maybe v1k1 and then v2k2, etc. Oh, this seems maybe a bit too complicated. All the way to λk gives you vk1 up to vk. Okay, let's call this n1 and then n2 and then nk. So the point is that you choose a basis for each eigenspace, and then the general solution is x equals C1 V11 e to the lambda 1t plus C, okay, maybe I'll make the indices match, C11 V11 e to the lambda 1t plus C12 V12 e to the lambda 1t plus dot 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 plus C1 N1 V1 N1 e to the lambda 1t. Okay, so basically you just pick eigenvectors for the first eigenvalue, and then you just repeat for the second eigenvalue. So C21 V21 e to the lambda 2t plus dot 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 plus C2 N2 V2 N2 e to the lambda 2t all the way to k. So CK1 VK1 e to the lambda kt plus dot 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 plus C K N K V K N K e to the k e to the lambda kt. Does that make sense? I mean, it basically your first eigenvalue lambda 1, let's say it has n sub 1 independent eigenvectors, right? So then you have, for each of those eigenvectors, you have a solution. And then for the second eigenvalue lambda 2, let's say it has n2 eigenvectors, linearly independent eigenvectors, then you just have a e to the lambda 2t for each of those eigenvectors, and then you just repeat until you get to the end. That's what this is saying. It just looks very complicated. So it just generalizes what we have here. So as long as your matrix is diagonalizable, and you can diagonalize the matrix, then you have an explicit description of the general solution of x prime equals ax. So remember, what are the matrices that are not diagonalizable? Well, those are the ones where, so if you have something like a matrix like 2, 1, 0, 2, like this is not diagonalizable. And we haven't discussed how to solve something like x prime equals 2, 1, 0, 2x. So this has a more complicated solution, and we'll talk about that later. But I also have to go over a bit about complex eigenvalues. So you can have complex eigenvalues where your matrix is diagonalizable, but you might have to work with complex entries. So for instance, you can have something like 0, 1, let's see, the first column is 0, 1, and the second column is negative 1, 0. So this is a very classic example. This is a rotation matrix, rotates by 90 degrees. And if you look at the characteristic polynomial, you get lambda squared plus 1. And that factors as lambda plus I times lambda minus I. So it has eigenvalues negative I and I. So we haven't discussed how to solve things like this. X prime equals 0, negative 1, 1, 0, x. So this matrix is diagonalizable over the complex numbers, but it's not diagonalizable over the real numbers. Like you can find n independent eigenvectors as long as you allow your eigenvectors to have complex components. So that's something we also need to discuss how to solve. But the story is complete when you have a diagonalizable matrix over the real numbers, right? It can be diagonalized over the real numbers. So you can write it in the form P, D, P inverse, where D is diagonal and has real entries, and P is a matrix with real entries. Because the matrix P consists of the eigenvectors, right, corresponding to eigenvalues on the matrix D. So for something like this, you don't actually need to do any calculus, because I mean, you might be asking, where is the calculus? We didn't do any calculus. You just use linear algebra. Well, the calculus comes from knowing that what you get is the general solution, right? So how do you know that you have n independent solutions and things like that? Or how do you know that there can't be any other solution? That's where all the calculus comes in. But if you take those facts for granted, then solving a system of differential equations where your matrix has constant coefficients just boils down to doing some linear algebra. Okay, that's what I wanted to say in this video.